All right, hello guys. Welcome back to my third video. The topic I'll be talking about is backpropagation. Before getting started, I'm kind of gonna give a recap about what I talked about in my previous two videos, just in case you guys didn't watch them, and just so you guys have kind of like a little background before I actually get started into the topic. And yeah, well, this video is mainly for my class CS 4540, also known as Intelligent Agents in Learning Environments. And my name is Adrian Flores, and let's begin. So I'm kind of gonna be talking about what I talked about in my previous two videos, which is pretty much using a neural network to actually predict handwritten digits using the neural network. When talking about the neural network, there's actually three types of layers that you guys should remember, which is the input layer, the hidden layer, and the output layer. The input layer consists of 784 neurons in this example. And the hidden layer is where the data is pretty much being processed and analyzing any patterns that it should watch out for. And in the output layer, uh, it consists of 10 neurons, which is from the digits 0 to 9. So depending on what number it guesses, right, it'll be either 2, 3, 4, and so on, right? But let's say in this example, the neural network isn't actually trained correctly, right? Let's say it's actually giving incorrect outputs, or in this case, giving multiple of the incorrect outputs, right? Because of uh, it's not sure which output is guessed correctly, right? So let's say we give the number two, right? And we want to guess uh which output it will give. So we give a handwritten number two, and we want to guess the number two, right? And let's say it gives it wrong, right? So this is where the cost comes into play, which where you would get the cost of the output it gives and the output you want, and you add up the squares of the differences between each component. And when doing so, this would actually give you the total cost for the example. And this is where we get our negative gradient, which allows us to change weights of the connections to be able to decrease the cost. So what is backpropagation, right? You can kind of think of it as an algorithm to compute um, the gradient of the cost function. So in this case, the magnitude of each gradient means how sensitive it actually is, depending on what the weight and the bias is. So you can see in this example, we have 3.20 and 0.10, right? Um, the one with the higher gradient would actually have a higher impact compared to the one with the lower gradient. So this pretty much means that 3.20 is 32 times stronger than 0.10. So even if we change 0.10 to like 0.3, it'll pretty much not really make a difference compared to if we change 3.20 to let's say 5.20, it'll actually have a bigger change compared to 0.10. And when talking about backpropagation, it also adjusts the weights and biases based on a single training example. So let's say the correct number we want to correctly guess is the number two, like I was saying before. But in the neural network that we have, it's pretty much highlighting multiple different neurons that aren't even correct, right? Because it this pretty much just means the neural network isn't actually very confident in being able to guess the right one. So this is where we actually have to change the weights and biases based on how far it is from the targeted value, which is the third one in this example. So all the ones all the way at the bottom, they don't really matter to us that much because they don't really affect the weight or the value of the targeted neuron. So in this case, we'll have to change the ones much closer, like the first two and the ones that come after it. So how is the neuron changed, right? How do we change the targeted neuron? Do we increase the bias, the weight, or the activation? In this case, I would have to say it's the activation, which I will talk about in just a bit. But there's some things you do have to remember, which is that the connections with the brighter neurons do have a bigger effect compared to the ones that aren't as bright. So in this case, like the black ones, they won't really have much of an effect. And the gradient descent does focus on what neuron gives you more bang for your buck. So in other words, pretty much depends on what neurons would actually have a higher impact to the ones that don't really have much of an impact at all, right? So when changing the activations in the previous layer, every neuron with the positive weight gets more brighter, and every neuron with the negative weight gets more dimmer. So like I was saying before, we are changing the activation for each neuron to greatly affect the neuron that we actually want to change. So we want to change the 0.2 neuron to a much more brighter neuron. So like in this example, we want it to look exactly like this one, right? And when doing so, we actually have to propagate backwards, right? So this pretty much means that we also want all the other neurons in the output to be less active. So in this example, we want only one neuron to be highlighted super bright instead of having multiple neurons highlighted bright. So in this case, each neuron in the output layer has its own desired changes, meaning that the changes are added together in proportion to the weights and how much each neuron has to change. So meaning that since we want all of these to go down and just have one to go up in the value of the neuron, we also have to change the values of the previous layer, meaning that we have to change either this one, this one, this one, and as you can see, the different amount of changes it has. So this one's going up, up, up. It keeps increasing, right? But this one keeps going down. So depending on what the output actually wants, it'll actually change the value for the previous neurons in the previous layer. And this is also applied recursively, meaning that we move backwards through the network. So from we start at the very end and then we end at the very beginning. So we kind of just backtrack our way back and change the previous neurons. And when actually analyzing all the training examples, instead of having to train every single individual one, which could be thousands or millions, we could instead split them up into randomly divided batches, also known as mini batches. So in this case, each step is actually computed based on each step batch, meaning that instead of just doing every single individual one, we are just analyzing a certain amount of individual data. So this could be like 10, for example. We are analyzing 10 at the same time, and doing so actually gives us a good approximation, but also allows us to have much greater computation speed up, which is actually what we want and is much more helpful and simpler. And I'll be talking about what are language models, right? What is an LLM, right? You could kind of think of it as a sophisticated mathematical function that pretty much predicts what word is going to come out next for any piece of text. It assigns a probability for all possible words that could be next, and depending on what word has the highest probability, it will be chosen right. So let's say we are trying to guess the sentence this one, right? So let's say we are trying to guess. You could think of a LLM as a sophisticated mathematical function, but instead of giving it the last word, we are making it guess the last word. So when doing the language model, it has kind of like a list saying like, oh, this word is more likely to be guessed, this one is less likely to be guessed, and so on. So the one with the higher percentage to be guessed, is the one that is chosen for the final word. So how are they trained? How are they trained and how do they learn? So in order to do so, it pretty much processes all the text that is pulled from the data. So it could be books, articles, websites, anything that is readable, it is given to the language model. And the output pretty much looks more natural when it actually selects some of the less likely words to be predicted in the output, which pretty much allows it to kind of like sound more like a human rather than a robot. And training you could kind of think of it as tuning the dials on a big machine. The whole machine actually, or the whole learning machine actually, or the whole learning model, sorry, actually depends greatly based upon the parameters, or also known as the weights. So if you change the parameter, it would actually change the probabilities on how the model would give an output. So that's very important to remember. And let's talk about how the parameters are actually refined. So each language model actually has hundreds of billions of parameters, which is a lot, a lot, a lot. And it's not manually made by humans. Instead, the algorithm is actually the one creating the parameters. So at first, let's say we want to train it, right? Let's say we want to make it much better. At first, the parameters are pretty much assigned randomly, right? So this pretty much allows us, the machine or the model, to just pretty much give lots of gibberish or lots of just nonsense, right? So in this case, we would actually make it analyze different types of sentences and then make it guess the last word for every sentence. And then when we have the word that is being guessed made by the machine or made by the model, we would actually compare the last word that it guesses to the correct guess to the correct last word from the actual article, right? So we would then compare them and then see how inaccurate it may be. And if it is accurate, then that's when backpropagation is actually used to tweak the parameters to make the machine more likely to choose the correct word. And when talking about the scale of computation, let's say if we were to be doing the amount of reading that the model actually does, it would actually take us about 100 million years to do so, which is quite a lot if I'm being honest. And when using chatbots, also known as language models, they also go through a different type of training, which is called reinforcement learning with human feedback. This is pretty much just workers behind the scenes just flagging any problematic or unhelpful predictions that the language model does make, allowing it to pretty much just make it more accurate and make it learn from its mistakes. And there's one thing to remember is that what are transformers? You could kind of think of it as every word on the sentence being given a list of integers, which pretty much signifies what word is going to be guessed depending on what it has, right? So as you can see, down has this list of integers, Bri has this list of integers, and depending on what it is, it'll guess the word. But there's one thing to remember that the words may change depending on the context of the sentence. So when you look at bank, you could think of money, right? You want to withdraw money, you want to deposit money, or you just want to do anything related to money in the bank. But when the machine actually looks at the other words, it may notice the word river, which completely changes that type of bank and will kind of think of a different type of bank, maybe related to water. So it all depends on the context of the sentence. And there are actually two types of artificial intelligence that I want to talk about, which is symbolic AI. This pretty much just follows the strict rules and logic that are followed, that are created by humans that pretty much give it its rules. So depending on what the humans make the rules, the artificial intelligence would actually follow them and use different ways to find different probabilities or any different type of moves, depending on what it's being used for. So in this case, IBM actually created a chess AI, also known as Deep Blue. It actually managed to beat the world champion, also known as Gary Kasparov, and it used different types of symbolic search algorithms to analyze millions of possible moves. So that's one cool thing that it could be used for. But another major AI that is actually very popular right now is the neural network, which is actually what I've been talking about in the previous three videos, including this video. And you could kind of think of it as an artificial intelligence that was inspired by how the brain works. The network pretty much learns from the data by adjusting its connections between the neurons, and it pretty much works using different types of layers, like I was talking about in the beginning of the video, like the input layer that takes the raw data, the hidden layer that processes data and detects patterns, and the output layer that makes the prediction. But in reality, it's way much more complicated than this. Like I was talking about in my other videos, there's a lot of things that have to be changed and a lot of things that have to be analyzed to be able to get the correct prediction, right? Even something minor, could create a difference for the actual output that is being guessed. And well, yeah, that should be it for my understanding of week 3. And hopefully you guys were able to enjoy. And thank you and have a good day.